Okay, let us start. So yesterday we considered the Newton's law of motions. Newton's law of motions. Yeah, which introduced the mass, inertia mass, so this mass, as I mentioned yesterday, it is a fundamental properties of, let's say, elementary particles. So the mass is used to characterize the fundamental properties of elementary particles. It means that we can distinguish the particle based on its mass. So that's the point. I mean, the Newton's law of motion introduced the quantity called mass, and it is important to us that this mass is related to the fundamental properties of a particle, elementary particle, especially elementary particle. Why? Because this is the building blocks of our universe. The universe made of these teeny elementary particles. Okay, so each particles, as observed in the laboratory, usually each particle has different mass. For example, if we have electron has a mass 9.1 times 10 to the minus 31 kilogram. But protons, for example, although this is the quark composites, the proton's mass is about 1.67 times 10 to the minus 27 kilogram. Okay, that's the difference. I mean, the elementary particle, we can distinguish, we can differentiate, we can distinguish them by measuring its mass. Okay, this is different from macroscopic point of view because, for example, a man, human, for example, the mass of the human is not unique like elementary particle. For example, if you have a weight, a mass, for example, 80 kilograms, then there are several people who have also their mass about 80 kilogram. That's not unique. Yeah, the properties of human. So, but there is also a unique property of a human. Well, so far it's unique. Every human in this earth have a unique properties. Can you mention it? What is it? What is it?
Fingerprint.
Yeah, fingerprint. Anyone else? Anything else besides fingerprint?
Our iris. Iris. Our eyes.
Your eyes, yeah, also unique. Anything else?
Our DNA, sir.
Yes, yes. Anything else?
Our DNA, sir.
Yeah, DNA also unique. Yeah. I mean, they have this. In general, they have the same properties, but in particular, you have a special case that distinguishes the other man from the others, another man to the others, a man to the others. Yeah, that's different. So, okay, so in this case, the mass introduced in Newton's law of motions is to characterize or to distinguish the particle, the elementary particle, not the human or animal like cat or something like that. Yeah. Microscopic animal, I think it's also not. I mean, they have distinguished by DNA, I think, or the structure of its cell, maybe, yeah, for microscopic animals or bacteria, something like that. Virus also has a distinguished properties like spike, protein spike, as you know, and also its inside this the skin of this virus, yeah, the DNA or RNA, yeah, that's also different. Okay, so the Newton's law of motion introduced the inertial mass. Okay, what I want to discuss today, there is also the property that also distinguishes the particle. That's what we call charge, electric charge. Sorry, electric charge. Q, electric charge. This is also to distinguish between particle. So each particle, for example, have different charge. So sorry, I forgot this M here is greater than 0. This Q here can less than 0 or negative, and this also, or it could be positive, yeah. Q greater than 0. Okay. For example, electron has a minus, yeah, electron, Q is minus E. Yeah. E is, we call it the fundamental charge. Yeah. 1.602 times 10 minus, sorry, 19, sorry, minus 19 Coulomb. C, usually we call it the Coulomb units. Okay. For example, and another example is proton, for example. Proton has a Q plus E. So this is positive. This is the nucleus, yeah, the nucleon, the core of the hydrogenic atoms, yeah, proton. Okay. So let me show you a table. Just 1 second. Okay. Can you see?
Yes, sir.
Yeah. So this is the standard model fundamental particles, which has been observed in the high energy accelerator. Yeah. We have the highest energy in the world is in CERN in Switzerland. So this is, we call it lepton. This is an electron. This is muon and tauon. Yeah. Tau is from tau. You add the on, then tauon becomes a particle. This is quark, which is the proton or neutron made of from quark. The composite, yeah, called composite. So this is the fundamental that form proton, neutron, and others heavy particle. We call it baryon. This is up, U is up, D is down, C is charm, S is trains, T mean top, B is bottom. This is force carriers. So this is for electromagnetic, this is for weak interactions, this is for strong interaction. Strong interaction. This called gluon is force carriers. So usually between quarks, they will exchange the interaction. They will emit gluon. Yeah, they will exchange gluon. And also, if we have electromagnetic interaction, usually each charge, for example, electrons between electrons, the interaction between electrons, for example, they will exchange gamma, a photon. So this is force carrier. I will show you. I will explain to you why this is force carriers. It's important to the interactions. Okay. And then, as you see, this is fermions. Fermion means spin half here. Spin half. So you see that this is a mass between neutrino and electron is also different, and also quark, right? And the quark has a fractional charge. Fractional charge. -1, 0, -1. So this is our fundamental particle. So what I said that this mass, yeah, from each particle is different, yeah? From neutrino, electron, muon, tau muon, yeah, tauon atau tau neutrino, yeah, etc. And also each quark also have different mass and also has a different charge. Yeah? Sometimes they have the same charge, but the mass is different. Okay, so it means that if we want to characterize the particle, electric charge is not enough, so you have to include the mass. Yeah. Okay. Any question? Okay, maybe save your question for later. Okay, as we explained about the interactions, what does mean interaction? So usually described by at least two particles. In classics, we said interaction, it means that the system contains at least two particles. If one particles, we call it self-interactions, but it is not known. I mean, it's not common in classical mechanics or classical physics. So usually self-interactions, we introduce the self-interaction in quantum mechanics, not in classical physics or classical mechanics. So in this case, the classical interaction means that we have, at least in the system, have two particles or two bodies. Okay. So what does it mean, electric interaction? If you have, for example, two charges, Q, okay, so the Coulomb observed that if they have distance r here, okay, from the experiments, the interaction also, let's say the intensity of the interaction. Intensity of interaction is proportional, so they have, it should be contains Q, big Q and little q here, okay? And also they observe that they also 1 over r squared, yeah, proportional to the 1 over r squared, okay? This is the intensity of the interaction. So Coulomb proposed the law that this intensity of the interaction can be described by the force of interaction. This is Q, BQ, Q little q, R squared. Okay, because this is proportional, so it should be, there is a constant here. The constant is 1 over 4 pi epsilon 0. Yeah. So, well, it's proper around 9 times 10 to the 9, yeah, if I'm not wrong. 10 to the 9, yeah.
I think yes, sir.
10 to the 9, yeah? Okay, yeah, 10 to the 9. Yeah. Newtons m squared over c squared. Okay, this in SI unit, yeah, SI units. So, can you tell about? So there is a question. There is a question because what I said that this is the interaction between two charges, BQ and the little q. As you, the statement here, yeah, F equal to K Q BQ little q over R squared. Okay. So the question is, does charge, when electric charge, yeah, because what I said about charge is in this case is electric charge. Electric. Sorry. There's an electric charge particle have a mass. So this is the question you have to figure it out. So let's see. Cynthia Rida.
Yes, sir.
So what is your answer about this question?
Um,
Do you understand the question, yeah?
that question, right? On the board.
Yes, yes. Does an electric charge particle have a mass?
I think yes, sir.
Why? I mean, how can you know? How can you say that the electric charge have a mass? An electric charge particle have a mass.
Mm,
Andra Fati.
Yes, sir.
Yeah. What is your answer about the question?
I think it has a mass.
Yes, why?
Yes, it has
How do you
electrons.
know? How do you know?
Because it has electrons, sir. Electron have a mass, right?
Okay, anyone? Reno?
Yes, sir.
Yes. Can you comment about the question?
I think it has a mass, sir, but
Yes. How do you know?
I'm not sure why.
You're not sure why.
Yes, sir.
But you cannot see from the columns below.
No.
Okay. Zahid Azmi Ibrahim. What is your answer? Oh yes, I have set. You have to log in to 6 to apa self presentation of self presensi presensi mandiri lah. You have to absen di mandiri ya until 2 o'clock. I set the time. Zahid, what is your answer?
I think it does have mass. What I know is that it will have either electrons or protons, in which I know that they have a constant mass for each electron or protons. So I assume that they would also have mass electric charge particles.
Okay, that's the fact. But can you see it from Coulomb's law?
Sorry, sir?
Okay, that's the fact. I mean, you know that electrons and protons have a mass. But that's the fact. But Coulomb's formulate his laws before humankind or people knows about elementary particles, such as an electron. So this is an old laws of physics. This Coulomb's law. Can you see it from the Coulomb's law? Without considering the fact.
Sir.
Bagas Irfan.
Yes, sir.
Yeah. What is your comment about Coulomb's law?
Since Coulomb's law states that this equals to force, hence
Sorry?
there will be a mass, because in order for there to be a force, there has to be some kind of mass.
Yeah, okay, thank you, very good. So this interaction, this is called force. It means that explicitly these two charges should have a mass. Why? Because in Newton's law of motion, the Newton's law of motion, okay, from this law, as I also mentioned yesterday, that if you consider the interaction to be the force, then your particle should have a mass. Okay. So this is what Coulomb said. Yeah. It means that every charged particle, electric charged particle, have a mass, but not the other around. I mean, the statement, for example, from if a charged particle is always massive, but not the other one. I mean, the massive particle is not always charged particle. Okay, you can see from the table I've shown you just now. Yeah, maybe I should show you again. Okay, this is the neutral is neutrino, but electron muon has a mass. Yeah, and this one always massive. Yeah, charged particle, fractional charge particle. So this is the fact. I mean, every charged particle has a mass. Okay. Any question? Any question? So in electromagnetic interaction, so this is called in general. Yeah, in general. This is called electromagnetic interaction. Yeah. So in microscopic point of view, let's see microscopic. That this electromagnetic interaction usually between particle, for example, Q, BQ, and little q, they will exchange, they will emit a photon, a virtual photon. Yeah. So they exchange the instruction. So they exchange the photons between them. Yeah. That indicates that this interaction is an electromagnetic interaction. So usually this we cannot detect because this is virtual, the photons. Yeah, photons, virtual photons. Virtual photons. They will exchange each other a photon. Yeah. So that's interaction means. So if you see the recent pandemic, COVID-19, yeah, it's also caused by interactions, right? Interaction between humans. At least two humans have interaction, okay? They will exchange, for example, the air they are breathing that contains virus, for example. That's why we have to WFH, work from home. So we have to isolate each other, not interacted with each other. Because this disease, yeah, this virus spread among peoples who have interaction each other. Yeah. Okay, and any questions? Any questions?
Not yet, sir.
Okay, not yet. Okay, let me see again. Okay. So this is what I said, this is the magnitude of the force. So if you want a complete picture, So the force is a vector, yeah? Vector. So you have to introduce the coordinates, for example. So this is the origin, 0. So the z-axis is perpendicular to this board, right? Outside, the direction is outside the board, okay? This z-axis. Okay, so this is Q, for example, BQ. This is Q. So let's say not BQ, maybe Q1 and Q2. It's better. Q1 and Q2. This is Q2. Okay. So this is R1, the vector, the position factor, positional factor of this first charge and the second charge. Let's say this R2. Okay. And from this factor, we can introduce the difference, yeah. This is R2 minus R1. Okay. So the formal formulation of Coulomb's law, this is factor, okay, Q1 over Q times Q2 over the magnitude of its difference, the displacement maybe, yeah, to 3, this is the magnitude, times the factor. Okay. So we can write that this R1 is x1 I plus x, sorry, y, y1 j hat z1 k. R2 is x2 I times plus y2 g, yeah, g plus z2k. Okay. So I had k, it's a unit vector. Vectors. Vectors. It means that the magnitude of factor I, j, k, 1. It's mean units. Okay. So the magnitude, for example, for R1 is square root x1 squared, x2 squared, x squared. Okay. So the magnitude of R2 minus R1 square root x2 1 minus x1 squared y2 minus y1 to z2 minus z1 squared. That's it. Okay. 2/3 means that x2 minus x1 squared sorry z squared to the 3 to through 2 here. Sorry, 3 over 2, sorry, the order. Okay, this is the formal. So this F, yeah, this F, what we can say is 2, 1, yeah. 2, 1 means, what means 2, 1? 2, 1 means the force X, sorry, the force X on Q2 caused by, sorry, caused this. Just 1 second. Caused, okay, just 1 second. It's hang. Hang.